Hey everyone. Let me start by thanking Gage and Elena for organizing this session. I'm really excited for all the talks and hope to see you all at some office hours or other events. So what I want to talk to you about today is branch cyclic covers. So those are three manifolds. And in particular, when are they L spaces? This will be joint work with Amarisa. So my goal for this slide is to tell you what an L space is. And to do that, I need to give you the barest of introduction to Heegard-Fleur homology. So briefly, it takes as input a three manifold with some adjectives, and via some complicated procedure, spits out a Z2 vector space. And how do you give it a three manifold? Well, you give it a nice decomposition called a Heegard splitting, which carries a lot of topological information, but kind of reduces the complexity that you have to deal with. And this vector space has a lot of topological information that we know of, most coming from gradings. But what we'll focus on in this talk is actually just the rank of this vector space. And it turns out that this rank is at least as large as first singular homology, is the order of that. And it can happen that you have equality. So a three manifold where you have the rank of Heegard-Fleur homology equaling the order of first singular homology, we'll call that an L space. And that, means that at least from a rank perspective, that manifold is as simple as possible from a Heegard-Fleur perspective. Okay, so you might ask, if you have a non-L space, so a complicated manifold, is it complicated in any other way? So geometrically or topologically? And we don't really know the answer to that question, but here's a conjecture in that direction. So parts of this are conjectured by different people. And what does it say? So if I have a three manifold, then conjecturally, it either has all of these properties or none of these properties. And what are these properties? So the first is what we've just been talking about. The manifold is complicated from Heegard-Fleur, from a perspective of Heegard-Fleur homology. The second says that the fundamental group has, you can put a total order on it that's invariant under multiplication on the left by elements of the group. And you can show that finite groups can never be left orderable. If you try to put a left order, you can show that you always get a contradiction. So at least if you assume that the fundamental group of a manifold is left orderable, you're throwing out manifolds with finite fundamental group, which are simple in some sense. And the last condition is that the manifold admits a nice decomposition by surfaces called a cooriented top foliation. So here's another kind of topological thing that Heegard-Fleur homology might be telling us about three manifolds. So hopefully that's enough context that you are somewhat interested in L spaces in which three manifolds are or aren't L spaces, with some measure of complexity. And the manifolds that we'll be interested in deciding whether they're L spaces or not are called branch cyclic covers. So let me give an example. So on the left, I have an annulus and an axis which pierces it in 2 points, this green line. And if I rotate 180 degrees about this axis and take the quotient, I get this disk, and I have two special points. And what's special about these 2 points is that they're the images of these two fixed green points on on the left. So each of those 2 points has only one preimage point, while all the other points in the disk downstairs have 2 preimage points. And in fact, away from these special points, it's actually a covering map, this quotient map. And then you can show that near the special points, you see kind of a nice behavior. So that's as close as I'll get to the definition of a branch cyclic cover, but that's the idea. And what is the cyclic? The cyclic is saying that we have this action by a cyclic group on the upstairs manifold. So this rotation by 180 degrees is the Z2 action on the annulus. Okay, and of course we're interested in 3 manifolds. So if I have a cyclic action, let's ignore that condition for now, and it acts by diffeomorphisms, by a diffeomorphism on the 3 manifold, then we get a branch cyclic covering map from the starting manifold to the quotient. And the fixed set upstairs you can show as a one submanifold, and so will the quotient be downstairs. So so the fixed set is a link in a 3 manifold. Going backwards, if I start with, let's say, a knot in S3, by some topological construction that's really beautiful, using ciphered surfaces of the knot, you can go backwards and produce 3 manifolds who branch cover S3 in a particular way. So these manifolds are constructed so that they have a Z mod n action where n is any positive integer I want, bigger than or equal to 2. And the quotient of that action is S3. And the quotient of the fixed set is the knot that we started with. So for each knot in S3, I have a well-defined set of manifolds for any index n larger than 2. And these are called the branch cyclic covers of K for each index n. So these are the manifolds that we'll be considering. They all have this Zn cyclic action. And of course, I want to know when these manifolds are L spaces. But I actually want to know a very particular type of behavior. So a knot in S3, if it has the property that this whole set of branch cyclic covers for any index, if all of them are L spaces, we'll call that knot a branched L space knot. So this definition should remind you, if you're familiar with this area, of an L space knot, and that's in the setting of Dane surgery, which is another construction of 3 manifolds. And there, the analogy is, if a knot produces infinitely many L spaces by surgery, it's called an L space knot. So here we're producing infinitely many L spaces by this branching procedure. Okay. And the theorem that I want to focus on today, joint with Ahmad, is that the pretzel knots pictured all have this property. All of their branch cyclic covers are L spaces. These are not the first examples. So Peters and Tarraghetto proved that, in separate work, in combined work, that these 2 bridge knots, they also have this property that all of their branch cyclic covers are L spaces. But these knots are all 2 bridge, which is a very special family, and in particular, they're all alternating. So our examples are the first examples which are non-alternating. And as far as we know, these are the only known examples, this 2 bridge family and our pretzel knot family. There also are some theorems which obstruct this property. So Rachel Roberts proved that if you have a fibered knot and this invariant of its monodromy, the fractional Dane twist coefficient, if that's non-zero, then there's some large enough n so that any branch cyclic cover with index larger than that is not an L space. And Boileau, Boyer, and Gordon show that, let's ignore this non-slice for a moment, they show that quasi-positive knots also have some index large enough where we know that the branch cyclic covers are not L spaces. And quasi-positivity is one way you can say it is that the knot has a certain type of braid presentation. So there's an example there, but I won't focus on it because we won't use it too much in the talk. And this non-slice condition, this is 4-dimensional property, and they asked whether that adjective is necessary. So just to rephrase our theorem again, we showed that these knots, all of their branch cyclic covers are L spaces, but more than that, they're classically known to be slice, and we show that some of them are quasi-positive. So that answers Boileau, Boyer, and Gordon's question by producing slice quasi-positive knots, which are branch L space knots. What are some things that make proving something like this hard? Here's a theorem of Ojvath and Savo, which is very useful, which says that alternating knots, we know that their double branch cover is an L space. It's one of the cleanest statements you can make about when branch cyclic covers are L spaces. And there's a couple of problems, which is our knots aren't alternating, so it's not even obvious from what I've told you now that even their double branch covers are L spaces. And of course, we're interested in higher branch cyclic covers, and this theorem only says something about double branch covers. So in part 2 of the talk, I will talk about how to get around these two issues in detail.